Good morning. In these few slides, I will try to present our proposition on using Holonic multi-agent architecture to deal with complexity in multi-modal emotion recognition. During the presentation, our background section will introduce the key concepts of affective computing. The related work section will detail the state of the art of the field for a better understanding of the problem. Then the proposition section will explain the use of Holonic multi-agent architecture to solve the studied problem. Our study is part of our works on affective computing, a computer science field that aims to enrich computer systems with an emotional layer. In fact, emotions have been long ignored during system design. To support emotions, a system must be able to recognize the emotional states of the user, then to use this information in an effective way. Both actions need an adequate emotion modeling and lexical definition for better classification and projection. Affective computing is a very rich but a very complex field. Many problems remain without answer in their root fields such as psychology and neuroscience. Therefore, almost every work focuses only on one facet or one approach without consideration for the complete process of affective computing. In fact, building one system that supports the complete process would be a very complex task. Therefore, we propose a Holonic multi-agent architecture to deal with this complexity. Let's take a look to this field and his key concepts. Affective computing refers to the integration of emotions in the design of computer systems in an attempt to make their systems more natural for humans to understand and to use. For a long time, the general belief was that emotions has only a negative impact on cognition. However, it has been proven that emotions can have a positive impact on cognition. Emotions play a very important role in our daily experience, and their consideration during system design can have a huge impact. Application domains can be the entertainment industry, video game industry, education, and even news and CRM systems. For example, affective computing in education finds its importance in the strong relationship between emotions and the cognitive processes like attention and memorization. The teacher can recognize the learner's emotional state as part of a human-to-human communication. Then he can adapt learning activities accordingly. However, in e-learning or distance education, the face-to-face communication is lost, with the big part of the emotional aspect in human communication. Therefore, it is very necessary to consider an affective layer on e-learning platforms. Affective computing is a very rich field with several theories, data sources, approaches, and applications. Data sources can be emails, audio recording, webcam input, social networks, and others. Approaches like speech processing, text processing, body gesture, and others. Every approach proposes different algorithms and techniques. Text processing, for example, can apply emotional word detection, NLP-based techniques, corpus-based techniques, and machine learning-based approaches. The emotional state can be used to adapt the content, adapt the navigation, or to express emotion as a reaction in virtual agents. In this work, we will focus on multi-modal recognition of emotions. These approaches attempt to support and implement the entire affective process from emotion recognition to emotion-based reaction. This goal imposes a certain level of complexity and heterogeneity. The first proposition was made in 2002, where speech processing approaches was associated to facial expression recognition approach. Then, a more complex proposition was made in 2005 with multiple approaches. Some mathematical models have been proposed to ensure a better combination of the different approaches. The vectorial model of Tayari Miftah is a good example. This proposition remain limited when compared to the fixed goals. The complexity of the field comes from first the input data that can be in different format from a unique source, one format from different source, or a complex object with several facets. Second, from recognition approaches that can be different but applied on the same piece of data. The Holonic multi-agent architecture can be the better choice to face this complexity and at the same time preserve a clear structuration that can preserve the effective process. The Holonic multi-agent architecture is based on the well-known notions that are the agent and the multi-agent system. It is defined based on the recursive modeling of agent groups. So basically, every agent can be seen as a multi-agent system itself. Holonic multi-agent systems showed better results and better modeling of the reality, and they are used in information systems, transportation systems, collaborative systems, and e-government. These characteristics are the foundation of our proposition. Our problem is the complexity and heterogeneity in multi-modal emotion recognition, and we propose the use of Holonic multi-agent architecture to support this complexity. We have followed the Sahib and Batoush process. Its axioms are well respected and preserved in our context. Agents are reactive. We have only local stimulus, and the design is centered on interaction and role. The system is itself a holon. It takes in input emotion-related data. It will give in output emotion-based reactions. Three categories of subholons can be defined: input subholon, emotion detection subholon, and reaction subholon. The input subholon will take in input the emotion-related data source. It will give in output emotion-related data source in a local representation. Several categories of subholons can be defined. Each agent is dedicated to a particular source and a particular data format. The processing subholon will take in input the emotion-related data and will give in output an estimation of the emotional state. Several categories of subholons can be defined. Each agent processes a particular data format and applies a particular approach. Finally, the reaction subholon will take in input the estimated emotional state and will give in output an application of emotion-based reaction. Several categories of subholons can be defined where each agent will apply a particular form of emotion-based reaction. Communication model is designed as a message queue communication mechanism. The design can be implemented on the different available multi-agent platforms. In addition, the system components must share a unique emotion model. Consequently, the system architecture will be as follows. We can observe that every level can be seen as a multi-agent system. The hierarchy deals with complexity in a simple and transparent way, and the effective process is well preserved. We have implemented a small prototype to demonstrate the feasibility of this architecture. Our goal was not the implementation of advanced approaches or to process complex data. Our goal was to respect the architecture. The prototype can be run with one processing agent that uses an emotional word detection approach. By introducing this particular sentence as input, we can see that the system gives in return an incorrect emotional value. The architecture allowed the extension and the instantiation of a second processing agent that will use the emoji-based approach. This time, the system is able to determine in a correct way the emotional value of the sentence. The code is available on this URL if you want to test and evaluate the approach yourself. In conclusion, our research field is affective computing. We try to apply the affective computing principles in e-learning context to support the entire process. The problem we find is with the complexity of the multi-modal emotion detection and reaction. We propose the use of Holonic multi-agent system due to their organization, extensibility, and flexibility. The proposed architecture defines 3 layers for the system lifecycle that are retrieving, emotion detection, and emotional reaction. Every layer is implemented using a multi-level Holonic organization that allows an efficient distribution of complexity and a progressive design. In the future works, we aim to enlarge the set of supported approaches, algorithms, and techniques. We aim also to ensure a full integration in an LLMS. We will support also the entire affective process during learning design, development, and runtime. Thank you for your attention.